Hello and welcome to Disseminate the Computer Science Research Podcast. As usual, Jack here. Today we are going to be talking to Eleni Zapradou, who is a PhD student at EPFL. And we're going to be talking about, let's see if I can pronounce this. This title is going to test my pronunciation of a few words. So, oligolithic cross-task optimizations across isolated workloads. So let's get started then. So welcome, Eleni.
Hello, thanks for having me, and very good pronunciation, by the way.
Thank you. Cool. So yeah, I'm really excited to chat to you today. So the usual thing we do when we start off is I kind of get you to tell me more about your story and how you kind of became interested in databases, database management research, and this really cool field that we all love.
So sure. Towards the end of my bachelor's, actually, I came to EPFL to do an internship with Professor Elamaki. And at the time, I was actually working on data cleaning. And this is really how I got exposed to research in general and database research more specifically. And I quite liked it, so I decided to come back for a PhD and work in the same lab. And a fun fact here is that in between actually my internship and starting my PhD, I worked on formal verification for the use case of autonomous driving. So a completely different topic. But at the end, I was more excited about working on systems. So here I am.
Fantastic. Yeah, so you had a nice little detour into formal verification and autonomous vehicle. That's really cool. So I'm guessing, what sort of things were you trying to verify there other than sort of, will this car not crash into other cars? Or was that sort of the general gist of it?
It was kind of like that. So basically the goal was you had some simulation with autonomous vehicles, and then you had to monitor them and basically have a way to actually tell whether some properties hold while the cars are driving around.
Okay, cool. So I guess, will we ever solve that problem? Because it feels like a pretty impossible problem to solve, right?
Yes, exactly. It's hard to define like what sort of properties you would want the cars to achieve. So, it was fun as well, but I think a bit too theoretical for my taste.
Yeah. Anyway, cool. So let's get talking about oligolithic cross-task optimizations across isolated workloads. And so let's start off by setting some context for this chat today. Then, so yeah, give us some background on the paper, and I guess sort of the main question here is kind of how organizations today use data sharing platforms and what are the sort of problems with the approach they use today.
Yes. So first, I would like to start by explaining what we actually mean when we say data sharing platforms in the paper. So a data sharing platform is basically common infrastructure that gives to multiple systems, or you could even think like multiple jobs of the same system, access to the same shared data. And so companies use these platforms in order to allow their teams to deploy many applications that operate concurrently on the same data, and they use the same infrastructure. So the ultimate goal here is basically for companies to be able to maximize the value they extract from data by being able to serve multiple business functions. And you can think that every business function could itself be composed of many subtasks. So this could be from a company like, let's say, Uber, that runs applications like fraud detection and monitoring, to a much smaller company like an e-commerce website, let's say, that has a dashboard and maybe it also has some recommendation system. So now, where does resource isolation come into play in this setup, actually? So all these different applications use the same data and infrastructure, but they can actually have very different performance requirements. So the problem then becomes that the performance of one task can affect the rest of the workload. And this problem is known as performance interference. And it is well known not only in database research, but in general for concurrent programming since the 1960s. And the solution that has been put into place for databases is resource isolation. And so this solution by now is very well rooted into database systems, I would say. So with resource isolation, essentially the system assigns a specific subset of resources to every task based on the requirements that this task has. And then the goal is to isolate basically tasks by enforcing these resource boundaries between them so that one task cannot affect the performance of the other. So you can think of resource negotiators and techniques like fair scheduling and stride scheduling as ways to enforce resource isolation. So now, since with resource isolation, we're provisioning separate resources for every task, as we increase the number of queries in our workload, we must also increase the number of resources that are available in the system. And in the past, this was quite okay, since with a small cluster, we could execute our workloads. But today, because we need to run more and more queries in the orders of, let's say, hundreds or even thousands, this becomes more and more expensive because we literally need to grow our infrastructure proportionally to concurrency. And in our community, there have been developed some techniques that we call cross-task optimization techniques, like, for example, data and work sharing, that have the goal of maximizing resource efficiency. Basically, you find some optimization opportunities across tasks, and then you use those to run the same amount of tasks with fewer resources. But the problem here is that these cross-task optimization techniques can actually penalize some individual queries. So then this makes them inapplicable in cases where it is critical to meet the performance needs of individual queries. Basically, to sum up, resource isolation is very expensive because of the high concurrency of today's workloads. And even further, it does not allow us to use cross-task optimizations that could actually make processing more resource efficient.
Awesome stuff. Yeah, so you've kind of got this problem of the noisy neighbor, right? Sort of interrupting my work. And it's funny, you see this a lot in kind of, I guess, cloud and multi-tenant environments with sort of various different things interfering, like one VM ooms and one process ooms and that causes something else to oom, and like totally separate applications. And yeah, so you said this was kind of becoming more and more of a problem with scale as well. So, and like kind of the number of concurrent queries and workloads that are running. So kind of to give us sort of a yardstick to measure, like what sort of scale are we talking here? Like what sort of a rough number when this becomes a really big problem?
Yeah, so actually, I think we're talking in the scale of hundreds to thousands of queries we're trying to run on the database system.
Cool. Yeah, that's pretty big. It might, yeah. That's that. This sort of thing, kind of doing the like adding more kind of resources, so you can keep doing the resource isolation approach. Might work well if you Google, right? But if you're sort of a smaller company, then it's not going to be feasible to kind of keep doing that. And we need another approach, right? So that kind of is a nice segue into your work and the kind of So tell us about kind of what the goal of your paper was, and then there's this really key concept in there called functional isolation. So yeah, tell us about that.
Right, yes. So as I said, we have these two options, right? In one case, we can isolate the resources for each query. But as I said before, this becomes more and more expensive. And in the other case, we can cross-optimize queries and maximize this way resource efficiency. But this way, we are risking penalizing some queries. Basically, with cross-task optimization, users really have no guarantees about the performance of their individual queries. And this is why in many cases, users would decide not to actually employ cross-optimization. So what we argue in the paper is that we don't really have to choose between resource efficiency and performance isolation, but rather we can actually do both. So users do not care per se about resource isolation, but rather resource isolation is just a way to ensure that all the queries will get the performance they need. And so what we call functional isolation is basically achieving the same performance metric as you would achieve if the queries were really isolated, but you actually might choose to use some of these cross-task optimization so that you are more resource efficient. Basically, an execution schedule would be functionally isolated when it provides the same or better performance when we compare it to isolated execution. So this means that what systems should be doing, instead of just using separate resources for every task, which does not scale and becomes very expensive, is to leverage cross-task optimizations only when these do not interfere with performance isolation. So essentially, the goal here is to selectively choose which cross-task optimization can you employ so that no query is penalized.
Awesome. That sounds great. Best of both worlds, right? We're getting the performance and we're more resource efficient. So let's talk about how you went about achieving this and sort of kind of determining which types of cross-task optimizations could be performed. And you did this in something called group share, right? So yeah, tell us more about group share, what it is and how it works.
Exactly, yes. So with group share, we wanted to test this vision for the specific case of work sharing across analytical queries. And so the goal for group share specifically is to achieve performance isolation and at the same time exploit opportunistically some of the work sharing opportunities in the workload so that we reduce the total processing time. So the key idea is that group share splits queries into sharing groups. So a sharing group is a set of queries that pool their resources together and share some common computation. And a critical condition for a group of queries to be a sharing group is that all the participating queries should achieve the same or lower latency when we compare it to isolate execution. So we basically have this twofold objective. On the one hand, we want at least the same latency as isolate execution. And on the other hand, we want to minimize total processing time. So putting it more simply, you can imagine sort of that all the queries are being egocentric. So in order for them to participate in a sharing group and share execution with other queries, they need to benefit from it. Otherwise, they want to be executed on their own. So we had two main challenges here when we're trying to design an algorithm to solve this problem. So the first challenge was a scalability challenge. Basically, the space of all the possible groupings is very big. So exhaustively just searching for the best grouping would be very, very expensive. And so we solved this scalability challenge by designing group share to be opportunistic. Basically, we avoid searching for the optimal grouping, and instead, the algorithm just focuses on finding just one grouping, one partition that consists of sharing groups, basically that doesn't penalize any query. So this was the first challenge. And then another challenge we had to solve is related to accuracy. So how do we actually evaluate whether a query would be penalized if it is part of a specific group a priori? So this would be quite hard because it would necessitate relying on cost estimation and intermediate cardinalities. And we know from database research that these are known to be inaccurate. So what we chose to do here is instead use runtime information. So basically, instead of trying to estimate a priori what would be the performance of a query in a particular group, we just measure at runtime the progress rate of the individual queries and also of the shared plans, and use these measurements in order to make decisions about how to group our queries. So these were the two main challenges, and I'll briefly say how the algorithm works. So overall, group share follows an iterative process. So initially, the algorithm will start by forming a very big group that contains all of the queries. And at any point in time, the algorithm will keep the groups sorted based on their processing rate. So your first group will be the slowest one, and the last group will be the one making the fastest progress. And then at every step of execution, the algorithm will identify the query that makes the slowest progress and its corresponding group, and it will check whether this query is being penalized. What does this mean? It means basically we want to check whether the query would run faster if it was being executed in isolation. And if this is the case, we move this query to the next group. Basically, at a high level, the idea here is if we find the query that is progressing too slow in its current group, we try the next group, which is progressing faster, and see whether this would work instead. So from time to time, we move basically groups around until we converge to some grouping that doesn't penalize any of the participating queries. And then from then onwards, we just continue with this grouping. Basically, I would say here that you can think of group share as a planner that decides what the groups are. And then you just use an existing work sharing algorithm to figure out execution schedule inside every group. And then you need a scheduler that will ensure that it will split fairly the CPU time across these groups.
Awesome, because that was going to be one of my questions, was like, once you've kind of got these groups and they're all sort of fixed by their processing time, essentially, what's the next step in terms of then being like, okay, how do I actually go and take this sort of these buckets I've got of jobs to then put them actually execute on the CPU? But you can use basically any work sharing algorithm you want after that point. Is that the kind of the way it would work? It's like you can
Yes,
plug and play
yes,
essentially.
exactly. So group share would be determining basically the limits inside which the work sharing algorithm can operate the groups. And then the work sharing algorithm decides for each group how to execute it. And then you pass this to a scheduler. You can use some scheduler that's achieving fair scheduling, let's say stride scheduling, so that you split the CPU across all these different groups.
Awesome. Another question as well when you was explaining it there was about when you determine whether someone's kind of the slowest in the group or the fastest in the group and you want to move it to a different group essentially, and you're trying to work out whether it's been penalized. How does it work?
Yes. So for this, we actually use the runtime statistics that I mentioned before. So what
Oh,
happens
okay.
is that from time to time, the system will actually run the queries in a sample of the data in isolation, just in order to measure how fast would I progress if I was running on my own.
Gotcha. Right. Okay. So we're periodically having this sample of, okay, this is actually my absolute runtime. This is how long it actually takes if I'm in the only person alone in the system and I've got all the resources I want. So we kind of have this ground truth, I guess, to sort of
Yes.
determine. And then you can compare it against, okay, nice, nice. Awesome. So there's a few things, and maybe we'll talk about this in the evaluate. We'll talk about the evaluation and the results. But I just wanted to ask up front, how does this scheme deal with sort of the dynamism in the workload and changing workloads over time? Does that disrupt the convergence and make the convergence slower? Sorry.
Right. Yes. So this is a very good question. And actually, for this paper, just to simplify the problem as a first step, we assume that we have a set of queries and these are fixed
Right.
and we receive all the queries in a batch. And also we assume that the data distribution across the entire table we're working on is the same.
Okay.
But the problem would become a lot more harder and also interesting if you raise these assumptions.
Yeah, yeah, for sure. Because I was thinking that if you are the example you gave at the top of the show about being, I don't know, you're having like a dashboard or some sort of kind of a limited set of queries, then that assumption probably holds quite true that like if you're Uber or whatever, your application isn't going to develop and change necessarily that fast for this to be a problem. But if you are running a generic platform that anyone can submit jobs to, then obviously you're kind of at the whim of the user, and there can be a lot more heterogeneity in the workload, and it can change a lot faster, I guess.
Right.
But okay, yeah, you've got to make some assumptions, right, to make some progress, and then you can always relax them
Yes.
later on,
Yes. I
right?
mean, this would still work if you have ad hoc queries. So if you don't know the query type,
Mhm.
but you would need to receive all the queries in a batch so that you find basically the work sharing opportunities within this batch. So you
Okay.
cannot assume that you have some sharing groups and then suddenly a new query appears and then you place it in one of these groups. Sort of
Sure.
you work with this batch of queries until you finish executing them.
Awesome stuff. Okay, cool. So let's talk about the evaluation then. So how did you go about evaluating this scheme? You mentioned it a second ago about there's a few assumptions you made, but yeah, tell us more about the evaluation and what that's experimental setup look like.
Yes. So we compare group share with resource isolation and also with full sharing.
Okay.
So basically, since here we're talking about CPU resources, resource isolation in this case is achieved via fair scheduling. So our first baseline is executing each query on its own. And we basically split fairly the CPU across all the queries. We use stride scheduling concretely. The second baseline is full sharing. Basically, this means that all the queries are being executed with a single shared schedule and all the common computation among the queries is being shared. So the objective here is to minimize the overall execution time while achieving the same or lower latency when we compare to fair scheduling.
Awesome. So what was the data, sorry, been used here and some of the queries? Like, do you have any sort of just like kind of a rough idea of what these queries actually were doing?
Yes. So for the data, we actually had synthetic data so that we can play around and kind of change the parameters and see how group share
Mhm.
performs. And then for the queries, you can think of a query type that has the shared part for us is a join, and then we have some extra operator after the join that might not be shared.
Okay, cool. So yeah, tell us about the results and how much better was it than the baselines?
Right. So how much better? Overall, we saw up to about 80% less CPU time without penalizing the performance of participating queries with group share. But of course, okay, this, how much CPU time we can save, it would depend on the amount of common work between the queries. And here an interesting aspect is that the more queries in your workload, then the higher the chances are that group share will be actually able to detect and employ some of the sharing opportunities. And then some other observations we had from the results are that we saw that full sharing penalizes short running queries while it benefits long running ones. So it is kind of unpredictable whether your individual query will get better performance or worse. And it more or less depends on what other queries are also running. And then another observation was that group share operates within smaller groups. So it forms these smaller groups inside which it can apply work sharing without penalizing the queries. And interestingly, group share doesn't only benefit the shared queries, but also the non-shared ones. And for the shared queries, you can imagine that they benefit because basically they participate in a sharing group. So they pool their resources together and also they eliminate some duplicate work. So you have more resources and you do less work. So great, this is where the benefit comes from. Now for the non-shared queries, why they benefit is actually because the shared queries run faster. So then the scheduler can actually allocate more CPU time to these non-shared queries. So this is an indirect benefit for the non-shared queries that they can also finish faster after all.
Nice. Yeah, they've got more. There's more capacity there for them to kind of do their work, right? So there's more stuff around, so they can. Oh, great! I'm going to use all these, and yeah, faster I go. That's
Exactly,
that's
exactly.
awesome. Yeah, and that's a nice, interesting observation about the more variety, I guess, there is in the workload, the more opportunity there is to sort of employ these optimizations and stuff. The thing that I was interested by is like how many sort of. I mean, and this is obviously very sensitive to the workload, but how many groups once it's sort of converged, how many different groups are we kind of talking about here? Is it like 10 groups, 5 groups, 100 groups? Obviously I know it's probably a function of the number of kind of tasks that have been run, but yeah.
Yeah, right. This is really hard to tell. It's very workload dependent.
Hmm.
In our cases, we didn't have many groups just because of the queries we tried.
Yeah.
But basically, in the best case scenario, you would have only a single group if really all of your queries are doing some common join, let's say, and then they can all benefit from being in this shared group, and perhaps resource pooling benefits all the queries so they can all be in the same group. And then in the worst case, really there is no work sharing opportunity you can use. So you can literally have as many groups as the number of queries. And then you're basically doing what fair scheduling would be doing.
Yeah. And how long was this period of convergence for to the number of groups that were optimal?
So for this, actually, we don't have an experiment in the paper, but more or less I saw that queries run for a few seconds and group share would always converge before that. So you
Oh,
would
yeah.
have enough time to converge and see the benefit. But I don't have an exact number on how many milliseconds convergence would take.
Yeah, but, I mean, it's in the magnitude of milliseconds, right? Which is negligible when you're
Yes.
talking about, I guess, these types of analytical workloads, right? Or whatever's working on top of them is yeah, milliseconds is fine. We can live with milliseconds. That's okay.
Okay. Okay.
It's
Great.
not hours or days, right? It's pretty quick. So
Yes.
yeah,
Yes. Yes. Yes.
cool. So this is obviously a very sort of what I'm trying to say. So yeah, this is kind of you've kind of proposed this initial work, and I guess I want to know kind of where you go next with this. And we spoke about some of the assumptions you've made. Is it to relax those assumptions and explore that space? Yeah, what's next?
So yes, one thing would be to relax the assumptions, and really this could mean also play with different, like experiment with different optimizations and different resources and performance metrics. For example, now in this work, we focused only on work sharing and CPU resources and then latency. But you could imagine other cases, like for example, let's say you have a use case where you have a couple of applications that are running and they're using some indexes and some other data structures. So with functional isolation, what you could do is share these caches and these data structures so that you save memory, while at the same time you can guarantee that all the applications meet their latency deadline. So one thing would be to basically really work with different types of optimizations and resources. And also one could take this problem into different types of workloads as well. For example, now we focused only on analytical queries, but the idea is more general. So it could be applied on streaming queries as well, perhaps even ML workloads. And the problem would become, of course, even more challenging if you think about mixed workloads.
Yeah, so that was going to be my sort of next. We've preempted my next question now. I was going to put my reviewer number 2 hat on and be like, what are the limitations with the work? And this is kind of all analytical queries. What about if we want to start doing different things? We want to start writing stuff as well. What happens there? But yeah, I guess you've answered that there. That's going to be something you look to tackle in future work. But kind of, I guess, the similar sort of question based off that though is, what do you think are the current limitations with this approach, and maybe with this approach in general?
Right. So one thing is, as I said, that we only consider CPU resources
Mm.
and only work sharing as a type of optimization. And
Mhm.
also group share requires the underlying system to be able to adaptively change the query plans. And this is something that there is a lot of research on it. So there are ways to do it to adaptively change the query plan, but on the other hand, it's not something that every single engine supports right now.
Right, okay, but yeah, that feels more like an engineering challenge to overcome rather than like that's doable for sure.
Yes.
Yeah, yeah, awesome stuff. Cool. So yeah, my next question is about the impact you think this work can have, or maybe already has had. So yeah, I guess what impact do you think it can have longer term, and has there been any impact in the short term?
Right. So really how I think about it is that without the idea of functional isolation, although cross-task optimization sounds tempting to use, developers would actually in many cases not use them because of practicality reasons and also because of the unpredictability they bring. Basically, you don't know what the effects will be on individual tasks.
Mhm.
So our goal with this work was really to give a framework to developers that allows them to employ different cross-task optimizations in order to use resources more efficiently. Basically, to be able to use all of this research that has been happening for cross-task optimizations without sacrificing performance isolation.
Nice, yeah, that's awesome, and I can definitely see it having a big impact on making it easier for people to access the latest sort of techniques and things. It can definitely be a massive win. So I look forward to seeing how it develops over the coming years for sure. So yeah, I mean, we off before we started recording, we kind of spoke about this being a slightly detour from your normal research, I guess. So has there been any surprises kind of dipping your toes into a slightly different area of data management? And yeah, what's the kind of most interesting thing you've learned whilst working on this project?
Right. So I think one interesting thing was that this is a problem where the search space is really huge.
Mm,
And so it's really a good example where you should not try to find the optimal solution, but rather just try to find a good enough solution, but do it as fast as you can. So convert to the groups as fast as you can. And this is something that Group Share achieves with this elegant iterative process that it is using to deterministically basically convert to the sharing groups. So this was one interesting lesson, I would say. And then another interesting thing is the importance of using runtime information rather than just trying to predict things a priori and like have these estimates that can be quite inaccurate.
yeah, definitely. I can see the way that the runtime sort of stuff, if you can collect that information efficiently and yeah, how you can use that to optimize various things. I guess is there a possible space as well for combining some of the upfront information with also the runtime stuff as well, and kind of having almost the best of both worlds there as well?
For sure, yes. So definitely, I think there is room to think of some sort of heuristic that would do some coarse grouping at the beginning, and then group share with the runtime information would only like do some small tweaks to make
Mm.
sure that the final grouping is actually consist of what we call sharing groups. So this would be definitely something interesting, and it could speed up the convergence.
Yeah, nice. Cool. Yeah, so I teased a second ago there that some of your other research is in a different area. So now would be a good time for you to tell the listeners all about the work you've done on stream processing. So yeah, the floor is yours, Lenny. Tell us all about it.
Yes. So as you said, my main line of research is on stream processing, and the overarching goal of my PhD is to enable scalable and efficient stream processing. So previously I was working on how to partition streaming data to the concurrent workers of a streaming engine in order basically to eliminate execution stragglers and essentially just maximize performance. And at the moment, we're actually working on applying ideas from the CIDR paper we have been talking about today to data streams. So the problem there becomes a lot more challenging because of the volatility of streams, but also due to the fact that streaming queries produce results on a window fashion. So you need to meet the requirements on every single window. So hopefully you will soon be able to read more about this problem, and we will share more stuff with the paper.
Fantastic. Yeah, we look forward for that to be to come out. You can come back on the podcast as well and tell us all about that once that's been published. So yeah,
that would be fantastic. Yes.
Yeah. Awesome stuff. So yeah, kind of going back to the current side of paper we've been talking about. How did this sort of come about then? What was the origin story here? It's like you say, it was different to your normal line of work. So how did this idea sort of synthesize? I know it's something you did with one of your friends and you kind of thought, yeah, let's do this. So yeah, what was that kind of like?
Right. So Panos, who is actually a co-author in the paper, was graduating at the time, close to graduation, and his PhD is on work sharing. So with his work, he really made work sharing a lot more practical. And so we were discussing about it, and we said that although not only work sharing, but in general, cross-task optimizations can make processing more resource efficient, people might still not be using it just because of the risk of penalizing some individual queries. And this is how we basically started discussing about this problem and trying to come up with a solution about it.
Awesome. Yeah. It's always nice when you can kind of work with one of your colleagues as well and something kind of away from your usual sort of space, right? And kind of, yeah, that's nice. You see these ideas synthesized and the serendipity of it almost. Yeah. So
yeah, definitely. You also learn a lot of stuff when you work on new things and with new collaborators. You definitely learn a lot.
Well, yeah, for sure. I mean, and you never know what techniques in your area can be applied to somebody else's area and vice versa, right? You can always be like, yeah, we could use, that looks very similar to problem X. Why don't I use that? And yes, for sure. And that's actually a nice little lead into this, my favorite question about the kind of creative process and how you go about sort of generating ideas and then choosing which ones to pursue. Because I mean, I have like loads of ideas which are just probably stupid and terrible and I need to discard them. But sometimes it's hard to let go of an idea you've had. So yeah, tell us about your creative process.
Right. I think this is the question that every PhD student has at the beginning of their PhD. Like, how do you come up with ideas? How do you choose?
Yeah.
So I think I'm actually quite lucky to be part of a very diverse lab where people work really on many different topics and are also very open to discuss. So I think this is a great environment to generate ideas, but also to test your ideas. Because as we said before, like you present an idea and then someone from a completely different perspective will criticize it. And this is very valuable feedback. So this is one way to come up with ideas. Another way is more like, one project sort of leads to the next. For example, here with this paper, we kind of limited a bit the scope so that we can actually solve the problem, but then you can raise an assumption and see how could you provide a more general solution or apply the same idea to a different type of workload.
Yeah, so kind of what I'm taking there from that is that the environment's really important. Been surrounded by super smart, clever people in a collaborative environment where there's always open discussion going on is definitely a big plus for kind of innovation, I guess, and for creating ideas. But then also, I like what you're saying about having, when you approach a problem, imposing some constraints initially and then solve it for n equals 2 before you then try and solve it. So it's like find the general solution, right? Kind of, and relax these assumptions iteratively and then explore the space. Otherwise, you'll go crazy trying to find the perfect solution straight away, right?
Yeah, definitely, definitely. Plus, another thing is when you work with on experimental research, you work on one topic and in one particular project, and you're trying to solve some particular aspect of the system, but then you observe different bottlenecks as well. So this is another way to get like an idea about the next project.
Yeah, that's it. There's projects keep coming along, coming along. So, and
Yeah.
there's kind of a sub question to what I asked a second ago about kind of, okay, these projects keep coming up, and this is a cool thing to pursue, and you get some important feedback from your colleague who've been like, maybe this is not a good idea for X, Y, and Z. But like, how do you, when you see a bottleneck, how do you know? Okay, how do you know not to pursue that specific thing straight away and be like, okay, maybe I should do this? And how do you avoid context switching constantly?
Uh, that's a hard question. I mean, I think personally for me, when I am working on a particular project and then I find different sort of bottlenecks, I just, I guess, focus on the goal ahead from the beginning and just
Yeah,
somehow try to minimize the effects of this new bottleneck I found,
yeah,
and then put it on a list of next tasks that I could do, next projects I could do. But sometimes the opposite happens. For example, when I started my PhD, I was working on data integration for
mm,
streaming data. And then there was this problem with load balancing, and really the approach I was designing was not performing well because of just load balancing. So
right.
this is how I ended up working on partitioning, and I never
Okay.
finished the project on data integration. So sometimes the opposite happens.
Yeah, I know. I just because personally, I'm a sucker for like, oh, new shiny thing, and then I get distracted and like I kind of forget about the thing I originally did, and I've gone down some massive rabbit hole. And but anyway, yeah, sometimes it works out, right? But yeah,
Yeah.
great stuff. So yeah, it's time for the last word now. So, what's the one thing you want the listener to take away from this podcast today?
So I would say that with this project, we're targeting the problem of having workloads with very high query concurrency. And why is this a problem? Is because processing all of these queries really puts a lot of pressure on databases. And if we continue to use resource isolation, this becomes very expensive. So our goal with this work was to show that there is actually a practical and robust solution that allows us to use cross-task optimizations while not penalizing individual queries. And we also highlight the importance of incorporating in a solution both the macro and micro view of performance, because I think this is really important for someone to actually use your solution. Basically, you shouldn't care about just the performance achieved for the entire workload, but also look at the performance of individual queries.
Well, thank you very much for speaking to us today, Eleni. It's been a fantastic chat. If the listener's interested, we'll link all of the relevant materials that we spoke about today in the show notes. And yeah, we'll see you all next time for some more awesome computer science research.